So as a quick aside, it's going to be easier for us to think about these various problems as decision problems versus some other sort of problem. So if you recall, a decision problem was a function where the output was just going to be a single bit. So when we look at this longest path problem, this was not a decision problem because the way that worked was we said, well, here's a graph, here's a start node, here's an end node. I want to know what is the length of the longest path from the start node to the end node. So the output to this was a number instead of a single bit, so longest path is not a decision problem. 3SAT, on the other hand, is a decision problem because we were asking this yes-no question: was the given formula satisfiable? So it's just going to be really, really easy for us to define our complexity classes going forward if we're looking exclusively at decision problems. So what we're going to do is we're going to be thinking about longest path as a decision problem. So we're going to figure out a way to modify this longest path problem so that it's a decision problem where its output is a single bit. So we're going to make like a yes-no version of this longest path problem. So in the original version of longest path, we were given a graph, a start node, and an end node, and we wanted to know what is the length of the longest path from the start to the end. So our input was three things: the graph, the start node, and the end node. And then our output was going to be a single number. To do a decision version, we're just going to come up with some way to modify it so that we're still sort of answering the same question in spirit, but we're rephrasing it to be a yes-no question instead. So for the longest path, one way that we could make that a decision problem is that we could say, well, given a graph and a start node and an end node and a number, is there a path that goes from the start node to the end node where the length of that path is at least the number that we gave? So now we have four values that we're giving as input: a graph, a start node, an end node, and a number in. And now this is a yes-no question. We just want to know, is there a path that's at least as long as in? And now notice that if we could solve in polynomial time the decision version of this problem, we're actually going to be able to solve the original version in polynomial time as well. Because what we did is we gave that target value in. The answer to the original problem is going to be the largest target value in, such that the answer is still going to be 1, such that there does exist a path of at least that length. So what we can do is we can use the decision version of the longest path problem as a subroutine to solve the original. So in order to solve the original, what we could do is we could just over and over and over and over again keep trying the decision version of the problem in order to find the largest value of n for which the decision version told us that there was a path of that length, because that's going to give us the longest path. So what we could do is we could try it for n is equal to 0, and then try it for n is equal to 1, and try it for n is equal to 2, and keep increasing n every single time until the first time we get a 0. Because once we get a 0, then we knew that the previous value for n was the largest value for which there did exist a longest path. So we can just return that. And now we can see that the maximum number of times we're going to have to go through this for loop is going to be the same as the number of nodes in our graph, meaning that if we could solve the longest path decision problem in polynomial time, then we only have v times more time required to solve the longest path original problem. So if longest path decision was polynomial, then the original longest path problem can be solved in polynomial time as well.